Josh Nathan. We're going to be talking about SoC exploitation. Yeah, quick agenda. What's SoC? Blah, blah, blah. We're going to get to it all. A nice plug. We are employed by Accufont Labs. I did that right?
Yeah.
Okay. So what's a SoC? We're going to just try to start at the real basics and get the whole crowd up to understanding what we did and how we did it. So sorry if we start a little slow. The SoC is a system on a chip. It's basically, instead of having a processor and then RAM and then flash, it's just boom, everything's in one package. You just solder it on and your phone boots as soon as you put a battery in it, or your power meter in this point. Pretty much everything these days is primarily running SoCs, unless you're talking about just a standard laptop. They're really nice because they're incredibly cheap and incredibly low power typically. The first thing you'll notice when you start playing with a lot of these embedded devices, though, is they actually do a shift from the von Neumann x8060 type architecture that you're used to playing with to a Harvard architecture. Kind of the same rules, kind of not. Things switch around. The main thing that the first kind of headache that you're going to see is just you have not one bus, you have two buses. And you have two buses because you actually have your code and data are basically physically stored in different places.
Yeah, when you look at the opcodes that are actually, doing what you're doing, the opcodes only go to like one place usually. So it'll depend on the architecture a little bit. And Harvard is kind of like a looser term than I think probably it used to be. But at least on the Teridian chips that we're going to be talking about today, they're very it's very explicit. I mean, these things are different spots physically inside the die on the SoC. As far as we can tell, we were never able to find any way to make them magically overlap or anything like that. So you can only talk to one or the other and not both, or not. You can never, for example, execute memory because the thing does it makes no sense, right? Like the execution pointer only points to one particular spot. There's no way to make it point somewhere else because these things don't overlap.
So, and I mean that, whereas there isn't an X, it kind of ends up acting like an X at that point. One of the cool, sexy, non-hacky things about the dual bus architecture is just it allows prefetch in parallel. So you actually are never waiting. There's never that bottleneck in the bus to actually get what you want because you're dealing with two buses. The buses can have different bit widths. It's a pain all around when you're dealing with that. And you got this crazy banking architecture that we've
but you end up fighting with it a lot. So when you're in any type of exploitation scenario, then it really matters. So what happens is that there's only, for example, a 16-bit width register to address what you want to address. And so basically, whenever you have an opcode that's going to operate on something, then on the Teridian architecture, there's like the first half is a bank that is always in place, and then the second half will be a bank that you swap out. And so you'll run certain types of commands that will swap out what memory is actually mapped at those addresses. And so when you're working in you're working in the Kiel compiler or something like that, you have very nice libraries that just magically make all that happen for you, and you never have to really think about it too much. You just know you call the right function, and then it just happens. But if you're in, for example, you're down in assembly in writing shellcode or something, then suddenly it's a huge pain because the compilers will naturally keep track of state of tons of things that you would now have to keep track of yourself and have to manually fix up. So it's a totally different headache than what you're used to when, like in a normal von Neumann architecture or something, where like everything's addressable and it's there. You don't have to do any special tricks to make something accessible at different times.
And that's kind of our that's kind of our 10-second introduction to Harvard. If you want to know more, probably the first place to jump to would be Neighbor Goodspeed's really good talk from Paris last month, 2 months ago.
Yeah, he just gave just a relatively short talk on exploiting tons of different types of microcontrollers, and he specifically covered the 8051 core, which is the core that's inside this Teridian chip, but it's the chip we've got is a little bit different than the stuff he talked about there. But then there's of course all the other stuff he talks about too, MSP430s and other fun things.
Yeah.
So we wanted to plug it.
It was a really great talk. just told Matt. Before we dig deeper into actual Teridian, we just wanted to do a very quick overview of hardware hacking for people that are more normally software, especially when you jump into the meter space. The first thing is we've heard every other presenter on meters talk about, you will electrocute the crap out of yourself. So be mindful. Our typical gear is just like everyone that's doing hardware. We're running logic analyzers. We're playing with debugging. The one big thing that we've seen a lot of people have problems with is just ground loops.
Yeah.
So here's a nice intro slide set up for what we're going to be talking about today. You can see in the close to you corner, we've got micro grippers on the actual SoC that's plugged into the meter, and we're doing live debugging. And we're doing live logic analysis. So just to kind of give you a better view into where we're starting.
If you're a software person that's never done hardware, all the concepts are exactly the same, right? It's just figuring out what are the things that you can influence, how do you get access to the data that you want to be able to see, how do you interpret that data, and then what can you influence to then start trying to cause faults. Sure. So talking specifically about the Teridian stuff, so these Teridian chips are made, let's see, there was Teridian Semiconductor was the original company. It was bought by Maxim a while ago, and they make a variety of different types of chips. The biggest sort of use case that we've seen out at least in the U.S. Is primarily all in smart meters, because there's so many smart meters out there now, and it's a relatively common platform for those. It's also, however, used in pin pads, so like the credit card pin pads, those kind of things. Distribution automation. If you're not in the power world, what that basically means is the back-end power shoveling that the power company does. So they're pushing more power to different areas to try to level set and keep brownouts from occurring, that kind of stuff. And so they have chips that are used in that stuff. And then also home automation, which is when this particular set of events occur, then I want to I want to raise or lower my blinds or something like that. On the Teridian side of smart meters, it's always on the metrology side. That's what it's designed for. So when we say that it's a SoC, right? It's got all the components that are needed to be doing metrology on a meter. So it's got all the stuff for analog power measurement and driving an LCD screen and the serial ports and all that kind of stuff all built into it. So it's always doing metrology, but one of the things that with smart meters, right, is that they're always talking to other stuff. They're usually in some sort of mesh network with other meters as well. And so that can either be done through some sort of dedicated daughter card, or it could be specifically done through logic on the Teridian talking directly to a radio chip. When they aren't hooked up to a radio, attack surface is a little different, right? So you have certain types of packets that will still terminate on the Teridian, so you're still going to get certain types of processing that would occur there. But in general, it is less, right? Because it's not doing raw processing on packets that you can send it. Whereas when it's hooked directly up to, say, a CC1110 or something like that, then in those cases you are able to play a lot more with the types of bad data that you can send it, and there's more opportunity for them to make mistakes. When you're looking at one of these and you're trying to figure out, okay, what are my active interfaces over which bugs might exist? How do I interact with this thing? They're basically just, there's an internal serial connection that's usually not exposed. That might be talking to a daughter card, or it might just be hanging loose, or it might be using it to control another component. There's the optical port on the outside. So those are that's actually just serial communications, but it's happening over infrared. You have to buy a special infrared dongle to do that, but it's the exact same protocol. It's just half duplex instead of full. And then internally, you'll see EPROMs, for example, for storing config data, things like that. And then occasionally you'll see a SPI slave port. That's pretty rare, but when you do see it, it's kind of a big problem, because as a SPI slave port, you can just directly reach in and read and write RAM. So if you ever see that, that's not good, at least from our perspective of caring about being able to read and write arbitrary data. But yeah, and then like I said, when I talk directly to a radio, suddenly it's a lot more interesting. So, when we started looking at these kind of things, as anybody who does work in any type a field like that, you realize, or out of any of the stuff that we do, it's oftentimes that you can't directly talk about the stuff that you work on a regular basis. And so we tried to figure out, well, how could we leverage this information on this and be able to come up with like exploitation scenarios, exploit code, and then be able to talk about it, give demos on it. And what we found is that, like everything else, they have specific demo boards that will show off a given particular chip. And they're really useful for getting it moving during the reversing process, like of a project, or also for doing something like this. And this is the one we're going to be talking about today. It's the 71M6533. It's just a particular one in that line. It's got very specific things that you would probably care about if you were like designing a meter. But from our perspective, we don't care about it too much, except for a couple things that we'll mention later.
We basically picked it because it was in stock when we were ordering.
Yeah, the ones that we wanted were like backward for 2.5 months or something, and they kept slipping the date on us. So finally, we just switched it. So give us this instead.
So a lot of times when you are actually dealing with a live meter and you're trying to get into the space and just figure out what's going on, kind of in a lot of hardware gigs, the first thing you want to do is dump firmware. And often we find that the SoCs are fairly locked down, and it's a pain to do that directly on device. So one of the first tricks that we pull if we immediately fail at pulling it off, like once we have to up our game a little bit, I tend to just take a hot air gun and or chip quick in this case. Go ahead and go to the next slide. Yeah, I just take chip quick on the actual meter and pull that chip off and then solder it back to the demo board, because the demo board's already broken out for debug, for ICE, for everything that you would want to do, because they're typically using that for development. So I just reverse it and I actually just solder the live meter SoC on there, at which point I can typically dump whatever I want. It's a nice, really lazy man's trick if you like to solder at all. And then since you've already blown that chip off, and now you've got kind of a dead meter that you're never going to use when you're starting to play with hardware again, I just take the hot air gun and I really remove every other thing off that PCB. So I've just got a bare PCB that then slaps into a flatbed and do some high-res images from there. And then throw those into the GIMP or Photoshop and start doing tracing. So
yeah, and on these they're still relatively simple. They're multi-layers, but usually your internal layers are just like ground planes or power or something, and so they're really not very complex. So it makes it simple to be able to start tracing out and figuring out what's talking to what.
Because a lot of times later when we talk about just like how to enable debug or how to do something like that, typically we're raising or lowering a pin or two. So it's nice to be able to get a good view into that board without just like staring at it, to get that quick reference of, okay, I need to solder here, or cut this trace, or blah, blah, blah.
So, we mentioned earlier, like just modifying one. That would be the normal use case. For some reason, a lot of times the guys that build these things think that they're being really fancy and doing things that are really hard. But in general, it's really not, right? So you just look at the data sheet. It'll tell you what you need to do. For this one, right, you have to unground a couple things. You've got to tie something off to 3.3 volts, stuff like that. It's relatively simple, and you can do it with a real small knife and making some cuts and using micro grippers or things like that if you don't want to just desolder the whole chip. When we're talking about the types of chips, so it is possible that you'll run into chips that you can't get a hold of, or for a variety of reasons, right? Like some of them, we run into some that don't even appear to exist in the documentation, but obviously they do. So you can figure out ones that are close to it. There's some other functionality that some of these support, which has trace buffers that will give you really nice execution flow once you get debugging interface up, but they don't all have that. And we didn't realize it when we swapped out the one that was on backorder with this one. This one doesn't actually have those, so we couldn't really use that for here, which is a big pain. But if you're looking at it, make sure you get the right one, because it's extremely useful for basically all forms of vulnerability hunting and exploit doing. So. And
they tend to release like a couple chips in the same series. So I mean, even if your target doesn't, you can at least at first pass you can end up working on the one with trace and then drop it.
Okay, so we're going to use this as an example to walk through kind of what Harvard architecture looks like on this. So this is going to be, right, we're going to start zooming in on this. Hopefully the resolution is high enough that we can kind of make out what we're talking about. But what this is just a functional block diagram showing about all the different components that are inside this SoC, and then we'll zoom in on kind of the stuff we care about from a security perspective and things that we want to begin to learn about and interface with. All right, so zooming in on this top part here. So these two components right here are they're basically cores that are executing functions. So, or executing opcodes, right? The one on the bottom is the MPU, that's the 8051 derivative. And then this one in the top is a computation engine that just does specific math basically for power measurement, right? It's doing very interesting types of, or I guess very accurate types of like floating point math and other things that we don't really care about for the most part. The 8051 inside this thing it's an 80515, which basically just means that, at least as far as I can tell, that the major difference is just that it's massively made more parallel. So it makes it a lot faster for the things they care about, but it doesn't really mess with us. So it's all the same instruction set. So if you know that, then you know it. It's byte aligned, which makes it useful for certain types of exploitation scenarios, right? Like ROP becomes more easy, becomes more possible. You don't have to worry about alignment, for example, because you have variable length instructions. And then the computation engine, as I mentioned, like we don't really care about what it's doing. We've looked at it a little bit of trying to figure out like being able to stuff other code in there that would maybe do other things that we care about. But for the most part, we're just kind of leaving it alone, except that you have to pay attention to it because it'll step on you. And that it shares flash memory, or it shares access to, well, it does share flash memory, but we don't care about that necessarily. But it shares access to X data as well. And if there are certain types of things that will block, and when you're in like assembly and you're writing your own stuff, then you're not ever checking those types of things, and you won't even necessarily see that interrupt occurred. So in general, we just kind of turn all that stuff off if we're ever doing anything sensitive that we want to make sure doesn't get messed up. Like writing to flash would be one of those things. Right. Okay. So talking about other components here, so we say that these are like physically separate things. As I understand it from talking to others that do more with like decapping these things, sometimes they're not physically separate. At least in this case, we were unable to find any way to make these things overlap. So as far as we know, they're totally separate. You've got flash, you've got XRAM, which is what you would consider like normal application RAM for the stuff you guys are familiar with. You have a very small portion of NVRAM, which just holds some settings, and then internal RAM, which is where your stack goes, and we'll kind of dive into each one of those. So here's the memory map. Right, so flash memory. This is where code and static data is stored. So a lot of this is dependent on what compiler you use. It seems like most everybody who develops on Teridian uses Keel, because Keel is what Teridian recommends, and they release source code for it, that kind of stuff. A flash memory, by default, can't normally be modified, right? Like that's part of the Harvard architecture. It's meant to be read-only, and 8051 was read-only for a very long time, apparently, until people realized that they needed to be able to do field upgrades, right? Like so, suddenly you're in a scenario where we want to put this thing in a device, where we want to put it out somewhere, and we're going to realize that we're going to have to patch this thing over time. We're going to have to fix it. And so they changed the architecture, and then they started allowing you to, via one way or another, modify flash. The thing is that it's very non-standard, so it'll be different on every 8051 architecture. And so we'll talk about specifically how Teridian did it here. But just as a general statement, yeah, you can't modify it. So let's see. Yeah, so it only addresses 64 KB at a time, and then uses bank switching to hit those other extended periods, other extended sections of memory. So flash is kind of weird if you're not used to it. If you don't know about how it necessarily works, there's some things that happen under the hood that matter when it comes time to do exploitation. Like if you're trying to modify flash RAM, I'm sorry, if you're trying to modify flash memory, and you're trying to say, for example, stuff your own code in there, then there are certain things that you just can't do. The way that the Teridian architecture works, the way that they recommend you do it is that basically you have to copy, like if you want to make a byte, like one bit change in a page, you copy that whole page into XRAM, right, and then make your modifications, and then mass erase the page back over here, and then you have to turn off interrupts and do all these other things to make flash suddenly writable, and then copy it back one byte at a time to do that. So that's a real big pain, right? Like if you're doing this with gadgets in ROP, for example, then that's like a relatively high bar to be able to find all the things to do that. And so we'll kind of talk a little bit about some of the ways around that when we get to the exploitation stuff here at the end. But the other side about Flash is that one of the sort of nuances of it is that you can unset bits. If you saw Josh's NAND talk, he kind of covered some of the same stuff there as well. But basically, it's that when the logical 1 or a 0, like when it's a 1, there is there's an electron inside that thing or whatever, right? And then so you can dump that out and you can make it a 0, so you can turn bits off, but you can't turn bits back on. The only way to turn bits back on is to do that mass erase, which sets everything to FF, which is all ones.
But once you've got FF, you can start dropping, 1 to 0 and at least create.
Right.
If you have a blank slate, you can create anything, but.
Right. So the obvious case there is that if they're all FFs, then you can write anything there because you're just going to turn off selected bits. But if it's like some other number, some other bit mask or whatever, then you can still turn off individual bits there and then create a different value. So you can still modify Flash in select cases. It's just not going to be general, and it'll be very situational on whether or not that is useful to you or not. On other architectures, it can be useful because sometimes the way they're organized, you'll have pointers up at the top that you can turn bits off and make the value jump lower, and then maybe you can modify things that are down below. So I know I can't remember which architecture it is, but one of them allows you to modify the data down below where it has a lower address space, and then the one that has a higher address space is read-only, read-only Flash. But you can flip those bits off, and then it'll allow you to jump down into the lower areas.
But we were the reverse.
Yeah, on Harvard, it's the opposite. So the way that Kiel does it anyway is that it starts right at the low address and then goes up. So there are still some cases where you can unset things to jump to a lower place in memory where it it may have had a series of 5 Fs, for example, something like that. But you're relatively small instruction sets that you'd be able to embed that way. All right, so the other stuff that matters on this particular platform, if you don't turn off the CE, then you get all kinds of garbled stuff, and you won't have any idea why it's not really working because you're not seeing the same types of you're not seeing in your debugger all the interrupts and things that are happening because you didn't know that you needed to pay attention to them. So the easiest thing is just to turn that stuff off. There's also there are additional flags that are meant to protect certain sections of memory from being accidentally overwritten. So one of the things that's funny, you start getting into the source code and their example code, and there's all these comments and stuff where they do their Flash updates where they do their in-field programming. There's every few lines there's some other value check where they're checking to make sure this thing equals this and this equals this and this equals this, because they say that just natural electromagnetic interference will glitch the execution pointer, and then it'll just suddenly jump into wherever, right? And if it jumps into the section of program that is modifying Flash, that's a really big deal, right? It'll corrupt your Flash, and then the whole thing will just get bricked. So for that reason, they put those checks there, but then they also allow you to say, I want to protect the first X pages of boot ROM or the first X pages of CE RAM or CE code. But they're just bits. So I mean, it's not really a security feature. It's more just of a thing to keep you from accidentally screwing something up. All right, so we said that you can unset bits. That Travis's presentation we talked about earlier covered a couple of those specific scenarios. So yeah, go take a look at that. Unfortunately, it didn't really impact us too much. All right, and then lastly, internal RAM. So internal RAM is really, really small. The stack on this thing is unbelievably tiny. And so what gets stored there are these special function registers, which are basically a whole bunch of switches that just tell you what the state of things and certain configuration items. Registers are stored there, and then very, very small data structures. But depending on the compiler, the stack is usually here, however. But like I said, the stack is really small. There's not much space in this area. So basically what the compiler does is that it sort of bridges the concept of a stack between the actual stack and then in X data. So what ends up happening is that the Kiel compiler will just hard link all these variable addresses from X data over here, but yet the stack's over here. So that has execution, command execution implications. So like if you're in an exploitation scenario, like whatever, pick your type of bug, you usually can't modify the stack, right? So like if it's you screwed up your mem copy, well, that's going to let me run off the end of where this buffer would be in X data, but there's nothing necessarily interesting stored there by definition, or that will always be there. Like on an x86 or something, you run off the end of it, and you can start stomping on all kinds of stuff, right? Because registers are mixed in with, with data, and in this case, that's not there. So it becomes much more nuanced and hard to figure out, like, okay, what types of things can we exploit here, and what types of bugs are still valid and that we need to be looking for. And then external RAM, that's the largest part, and or the largest part where data goes anyway. And this is where your operations interact with. So anytime you find a vulnerability, if you find a crash, it's usually always in XRAM. You're finding some way that you're either corrupting XRAM, which then causes something else to crash, and then eventually it'll trigger some sort of an interrupt that resets it. Or you can get extreme control of it in certain types of scenarios. All right, and this last piece, this is the emulator, and we just kind of bring it out because it is a separate component that has its own sort of security features that turn it on and off. Yeah.
So the actual Teridian chip itself probably could have supported a lot of more easy, convenient things, but they decided that they were going to run with ICE. And it's this like fairly crazy, completely undocumented, well, pseudo-undocumented debugging interface. The really annoying thing is it requires like a $1,200 device just to debug the thing. And we'll get into the chip interaction when we talk about glitching. So, but inside it, it's just really a simple Spartan. So it's a very expensive FPGA. We get into it now. So ICE, when the chip's actually when you hit it with VDD and you're actually powering on, you get a pre-boot phase, which is either 30 or 60 instructions, basically clock ticks, right?
Right. And this is the Teridian, right?
Yeah.
So when the Teridian first boots, it begins what's called a pre-boot phase of either 30 or 60, depending on the chip or depending on which documentation you believe. And then at the end of that phase, then it will allow the debugging interface to be enabled if you've not turned it off, basically.
Yeah. And so Teridian's suggestion, which I guess that's what we'll get to in glitching later, is that it's really the third instruction in that 30 to 60 instruction set that they suggest. Thou shalt turn off ICE so you cannot debug. And there are ways around that, but it's definitely a pretty tight window.
Yeah, it's kind of an interesting security decision, right? That it's going to be on by default always unless you explicitly turn it off. So that makes all kinds of options for well, how can we maybe convince this thing to not turn it off, right? Whereas like blowing a JTAG fuse or something, it becomes much more hard. Like you may not even be able to turn it back on at all. You may have to like decap it and like do some ridiculous stuff that half the people in here do, but I certainly don't do. And so it's much harder to turn that kind of stuff back on than it would be on this particular architecture.
Yeah. So, and I mean, when you shift over to the other markets that Maxim Teridian is in, like the pin pads, they typically go back with a more standard JTAG fuse from what we've seen, right?
Yeah, it's supposed to be a one-way flip that can never be unset. We've not looked at it yet, so I don't know, but that's what their documentation says. All right, and so here, these sections we're talking about the interfaces that are in, right? So these are the two UARTs, and then I guess I didn't highlight the EEPROM and the SPI slave, but that stuff's on there too. So when you're looking at the chip, this is the kind of stuff that you're interacting with, or you're tracing back out on the board. So you're trying to figure out, okay, well, how can I get data into these things in a real-life environment? And this is where all your vulnerabilities are going to be. So we talked about the optical port a little bit earlier. I mentioned that. If you look up, let's see, I think I plug it here. Yeah, so this guy Cutaway gave a talk on that optical serial port. And the short answer is that there's just bugs everywhere, right? Like it's really hard to fuzz it and keep the machine up in any sort of state. It just crashes it crashes like crazy. So that's kind of your standard for code quality there. Now, that whether or not you can exploit those things may be different, right? That's some of what we're talking about today. What are the vectors that you could actually use a crash like that to figure out, is it actually potentially exploitable, and how would we go about that? But these are the types of ways that that's going to come through, right? So it's either going to be, like walking up to the thing and doing it on the outside. And any bugs you find on the outside are also likely to be on whatever the networking protocol is that's on the inside, because they only use one protocol to talk, right? So there may be some different wrappers around it, but ultimately it's processing the same types of packets. Right, so the one on the outside, cutaways talk, go take a look at it. And then, yeah, any bugs that you find via like fuzzing on the outside, or that you find via those types of ports are also on the inside. All right, so talking specifically about how do you do exploitation on this stuff? So this is that secure bit that we mentioned earlier that will prevent the reading of flash memory and CE program RAM. It's reset on it is reset to 0 on every chip reset, and you have to manually set it to a 1 during that pre-boot phase, or otherwise there's some sort of a window when I would be able to interrupt execution and stop you from being able to set that. Right. So mass erase, it sets all the flash to FF. So that's the only way that you're supposed to be able to get a chip back after you flip this bit. So when you connect it up to a debugger, this window will pop up that looks like this, and it'll say, hey, we're in secure mode, I can't do anything. The only thing that you can do is you can do a mass erase. And so doing a mass erase, of course, wipes out all the code, so then you lose the code. But the question is, did they think to do the other stuff too, right? Like there's other things that are on this that we may care about, for example, on the different types of RAM that are there. And on this one, they don't. So here's just a little picture of that, right? So if you set it, the one on the left, it gives you all zeros. It's saying, hey, there's no data here. I can't give you anything. But then as soon as you do a flash erase and do a reset, then all that data is still there. So that's important to remember, because what will often happen during, say, encryption algorithms or encryption implementations, that they'll pick up data out of like a read-only location, like maybe code, and they'll grab, say, encryption keys from there, and they'll copy them into RAM. Then, of course, that stuff's also in use while it's doing processing. So there are lots of ways to be able to see that stuff there, be able to trigger certain types of procedures on the chip, and then cause it to do a mass erase and reset, and then you can recover that data. So right, XRAM is accessible. Once you do that, power is never lost to XRAM, so even though it's volatile, it doesn't really matter. And then, yeah, where did you think to store this stuff? Is it accessible through here, or is it not? All right, so code execution on this. Right, there's no concept of executing RAM. Right, the opcodes don't work that way. When you jump to a 16-bit variable, you jump to this number, it only goes in the code location. There's no way to make it go anywhere else. So you can't execute the stuff that you can modify. And because the stacks over here in the internal data and then variables are over here in external data, normal vulnerabilities are really hard to exploit. So any sort of, like I said, the buffer overflow types of scenarios become very difficult, because let's say you get even full and complete arbitrary control of whatever's after your buffer. That's still relatively a high bar to then reach into memory and then make selected modifications just on RAM that then will then turn you back into what you care about. So right, so there are ways. Well, we'll get to that here in a second. So right, standard overflow, they're in different places, and you can't do it. It's not necessarily an 8051 specific thing, because there are other 8051 architectures where apparently you can do that, where the stack has variables on it. And so therefore, when you are interacting with those variables and they screw something up, then you can corrupt like your stack pointer, for example. And you can take advantage of the single byte alignment and then go do ROP chains and all that kind of stuff that we know about. It would still be painful even if that were available on this platform, just because of all the hoops you have to go through to be able to modify flash RAM or flash memory. But at least it would be doable. But on this, it's not, because of how the compiler works. And so like the compiler knows how all this stuff works, of course. And so it just does hard links to all these places. So it's sort of like if every time a function is executed, then the variables that are going into that function are always stored in the exact same place. So if you can get a copy of all of the code that's executing, and if you can figure out a vulnerability that gives you a large amount of control over that, then you may still have some options, like this type of vulnerability. So this is actually perhaps relatively common on this kind of stuff. You think about when you're implementing a spec that, like the spec that's used over that optical port, and it's used to shovel metrology data back and forth. It's called ANSI 1219. And it uses this concept of tables, and basically it's these huge tables that have variables in them, and then you store some things in them and you read some things from them. And that's how the smart meter knows, or that's how the power company knows how much power usage your smart meter is using. If you think about how would you implement that? Well, it's probably going to be in large arrays, and you're probably not going to necessarily care about if somebody asks for an element that's not in that array normally, because it's not anything that would ever happen in any normal use case. So when you're implementing a spec, and the spec says that these are the order of the items in this table, there's never going to be a scenario where you're going to where you're going to ask for a negative one, or you're going to ask for one above, you're going to wrap it, things like that. So what we did is for this we re-implemented this bug in this hardware. So basically there's a function accessible over the serial port that has this basic exact thing. It has both a read and a write version. So it allows you to give it a number that becomes the index in the array, and it'll let you either read that back out, or you can give it a value, and then it'll write that to that location. So at that point, now because it's a 16-bit field and there's only 16 bits of address space, you can now modify anything in Flash, right? So, anything in Xdata. You can, of course, you just wrap it back around if you want to get to stuff behind you, and you can make whatever modifications you want. But how do you know what to write to, right? So even if you've got arbitrary locations and you can read and write to it, it's still not necessarily simple, right? I mean, it's sort of like, if you remember, I've seen exploits that were written a long time ago that were I don't think they even would ever work, but I've seen people like come into IRC and stuff and be like, hey, I'm trying to make this thing work, and they've got a scenario where they can make arbitrary changes to the stack, and they're just like trying to reach into the stack and just modify things. And like that would never work in the stack, because the stack is very crazy, right? It's moving all the time. And so you need some sort of context to know where to make the types of modifications you want to make. And here, everything's fixed. So if you can get access to the code, then you can find out where those variables are supposed to be. Now that doesn't mean that memory location is not going to be shared by something else. So you still have like timing issues. But in general, if you can make certain types of modifications, and you can find some place there that will give you execution flow that will let you like call to something, then you could feasibly set it up so that you can actually run whatever functions you want, whether they be sort of ROP style, that they don't actually exist, or they don't exist normally, or if you want them to be just where ones that were already there in memory. So how do you find something to modify, right? So you've got to find some sort of a pointer that is then going to get later pulled into the code on the other side to then get executed. That's the only way you're going to be able to do it. It took a while, but I finally found that one thing that seems to be relatively common is this concept of a software timer interrupt. So what they did is that, so this hardware I think has three hardware timer interrupts on them. And so if you don't know what that means, basically you can say, hey, whenever this amount of time goes by, or this number of clock cycles go by, I want you to do something, right? I want you to execute this block and do something. Well, so what they do with a software timer interrupt is they can take one hardware interrupt and they can multiplex it into 8, I believe in this case. So basically it just has the hardware timer interrupt running at a really fast loop, and every time it fires, it goes and then it checks a bunch of other things, like it checks some arrays of other values that are associated with that software timer interrupt, and then it'll decide whether or not it needs to fire additional code or not. So it seems to be a common way, right? And so between, like the way this is called, so when you want to register a new one, basically what you're doing is you're saying, okay, I want to register this new software timer interrupt. I want it to fire after X number of cycles or some period of time, and I want it to jump to this particular address, right? I want it to execute this function. So those are all stored in arrays in Xdata. So if you can modify Xdata, you can do it. Doing it this way, you still have there are real life considerations that make it real painful though. So when I was doing exploitation and I was trying to write all this stuff, it was really painful because you don't, even if you shorten the window. So again, you control all these things, right? So you can shorten the number of cycles that it's looking for. So you can say, like, I want you to execute, every cycle or whatever, and then it'll execute on the next hardware interrupt, next hardware timer interrupt, whenever that fires. But even then, the thing with at least with the Keel compiler is that it's storing lots of stuff in Xdata right on top of each other. So you reach in with the vulnerability one time, and you write the arguments that you want them. You put those somewhere that you want them to be to start setting up your function call where you're eventually going to get. You write these, you write these, you write these, and then you finally go in and you overwrite this pointer that's actually going to give you execution. And by that time, RAM's already been modified, right? So whenever that happens, then worst case scenario is that maybe you're doing some sort of flash write operation, and the arguments that were being passed to flash write are now corrupted. Right? So you think what that would do, right? Suddenly it's writing something unknown to some other unknown section of Flash, which is a really, really bad scenario for all exploitation scenarios. All right, so constraints, right? What do you have to do to be able to do this? So even if you're able to overwrite pointers like this, you're able to set things up so you can actually get arbitrary function calls of whatever type you want, you still can't really modify Flash, right? You've got to go through all these steps to do that. You've got to unset those bits. If you're trying to write back to a protected ROM region, you've got to flip a particular bit that changes how the MoveX statement works. So by default, the MoveX opcode, what it does is it basically says, hey, grab this over here, and I want you to move it into Xdata over here. When you flip a particular bit, suddenly the MoveX command now operates differently. It grabs from over here, and then it will actually write to Flash, assuming it meets the constraints we talked about earlier about you only can drain bits out of a field. You can't add bits in. So you've got all these steps you've got to go through, and it makes it relatively difficult. At least if you're doing it from a gadget perspective, right? Real life ones are a little bit easier because when you're looking at an actual meter, then it will already have this code in place somewhere. So it depends on where you can jump into it. It depends on what types of things they're doing after it and what types of checks they're performing. But it's still usually possible to just leverage their code as well in any real-life scenario. But feasibly, you could do it all yourself via ROP chains or something. ROP chains. They're not really ROP chains in this case, but they're conceptually similar. But it's really difficult. And then the other thing is that at least on this software timer interrupt implementation, it only will execute functions in that first 64K. Basically, they said, we don't want to mess with this whole banking architecture. It's really difficult. And so that further reduces the code that you can reach, basically. So if you want to, let's say that you discover, oh, there's this function over here that would be really useful for me to call, but it's in a different bank, then that makes it harder, right? Then now you have to figure out how to swap the bank without the whole thing crashing before your function is called. But 64K, even though it's small, still usually will have enough of the stuff that you care about, especially in a ROM scenario where if you are the manufacturer that you're coding this thing to allow you to be able to update it in the field. Well, that's the exact code that you're going to put in that first block that is going to be accessible, right? It's going to be right in that very first page because one, you want to protect it from being accidentally overwritten or being overwritten during your upgrade process. But two, it'll be accessible via these types of things. So there's other limitations that just don't want to deal with banking. And so that's why the first few pages are kind of important, and that's why they allow you to protect them differently than they do the rest. So, so code block exists that will allow you to do a lot of the heavy lifting, so you want to always try to find those. If you find exploitation, you want to look for those particular patterns. Like in this case, you know that it's going to do stuff like it's going to turn off interrupts, it's going to turn off the CE, it's going to flip this particular bit, and those types of instructions are going to be very rare. So you can usually find it even if you don't have source or something. Yeah. Okay, so you probably
There's no way.
Probably can't read this. Okay, so this is the Stm code. So I was just going to kind of step through that a little bit and talk about leveraging the software timer interrupt and those arrays there to be able to do this type of exploitation. So really, I guess there's just the two major sections that you care about, right? That you give it how many counts you want it to go, do you want it to restart or not, and then what's the function pointer that you want it to call when it gets there. And then it adds it to an array. And then down below, after the hardware timer interrupt has flowed through, then it'll hit this point eventually where it converts that function pointer out and calls it. It's called by a lot of places. So the other thing that can be nice is that, let's say that you can't directly call a piece of code because it's in a different bank, right? So that can happen here and does happen in some cases here. All the places that call it will also have all that internal logic to switch out the banks for you and take care of everything for you. So if you can find the other places that are calling it, you might be able to set up their variables in such a way that it allows all that just to flow through and happen. The other nice side about it is that sometimes you'll see that the variables that are being, or I guess the data types that are being used to store the data that eventually gets into a call is different than the data type required by the function. So I've seen that in some cases where, for example, the function may require, like one of the fields could be, like the address field, could be stored in internal RAM. And that's going to be a big pain because you don't have access to internal RAM. You can't modify that directly. But there's a place over here where they're copying from, like the way it would normally work, some interface, it pulls this data in, it parses it, and it parses that into an X-data field, and then that gets pushed over to internal RAM, and then the actual function's called. So you can usually chain back up and find some place where this stuff is stored in external data that you can modify. Right, so this array of functions. Addresses are always static for a given compile, so they're always the same across all meters. So if you figure out how to do it on one, you can do it on all the others. And then all you have to do is figure out what index value do you have to feed to that type of vulnerability that will allow you to execute or to modify the given part of memory that you care about. Right. The only thing here that the STM stuff directly, you have execution, but you don't have any contextual information about anything else really. So you're kind of shooting blind, and you don't really know what else is happening, so which can make it kind of risky. So there are different things you can do to try to make it more stable. You can shorten those timing windows as much as you can. There are other ways that you can disable interrupts. In some cases, depending on how it's firing, sometimes if you disable interrupts, then it will no longer process your input, which would really suck. So there are things like that to look for, at least, if you're having a stability problem. Okay, so our demo stuff here, we have a hardware problem on the number of USB ports that can be plugged in next to this cable, so we kind of have to like swap around here. It's going to be kind of silly. And really all we're showing here, and we can go into as much detail as anybody wants later, but all we're doing is we're leveraging the types of stuff we talked about here to write shellcode to flash memory and then jump to it. This particular one, I was working on the shellcode last night, and the state at the time of the function call is where the banks are in a weird state, and so the things that I want to call are in the wrong bank, and I can't yet get it all set up correctly so it doesn't just crash. So we don't have a cool flashy demo, but we have it's obvious that we're modifying flash memory like you're not supposed to, and then we're able to jump to it.
Ready?
So, yep. Oh. Right, so each one of those is modifying the arguments that are going to something, and then finally executing individual functions by beating up on the STM array. And so the first one will go ahead and do the flash write. Then you basically wait for that to occur, and then after that you have to fix up the STM array, because if you don't, then it has a pointer that's pointing to a flash write function that's just sitting there that's firing all the time. So that's really bad. Like your whole world just gets corrupted very quickly if you don't fix that up. And then finally you just jump to where you're actually going. And then, so sorry for the laying back and forth. And there's not much to it, but this is a flash part of RAM that is not supposed to. So it's normally all FFs. Basically, I'm jumping to a high part that's not been modified yet. And then I did it. Oh, and this one actually got corrupted on the way over. So this is part of it. I've got other code that will sort of try to normalize the environment first. So you can, there are little tricks you can do, like you want to make sure you trigger a reset and then wait a certain period of time for things to kind of settle down. And this whole time we've been talking, we've had this board sitting up here running. So it has time to get into a different state than what we're used to, basically. So the timing values that we're using don't always work. And so this is supposed to be, this field right here at 6001 is not supposed to be an FF. I forget what it's supposed to be. It's whatever in my shellcode. But that changes that entire instruction, and so this makes gibberish no sense. Yeah. But this is a naive implementation to fix the bank that's in use and then jump to a piece of code that I care about. But when I get there, then nothing works correctly because it's all wrong. So it doesn't actually work. But we're sitting here with resident code execution here, and so now this is here forever. And so if I were to have modified another pointer up in memory somewhere by either now that I've got this, I've got a stager, so I can do anything that I want, right? I can do the fancy recommended way of copying out the whole page of memory and then making modifications and moving it back in, or I can just reach up and I can selectively unset bits to move a pointer to jump down into my code to make sure my code executes every whenever I want it to, right? I can tie it to some sort of an interrupt. I can tie it to just make sure it runs every time it boots, whatever you want. So, all right, and that's. Cool. Oh no, we can talk about. We're not done. All right.
We've got 6 minutes, man.
Keep going.
Hey, so we wanted to take questions, so I'm going to try to run through this really, really fast. And this is actually mostly kind of ongoing / future work. But like we said earlier, we've got that preboot section that basically, if they flip the bit, and that's the nice Teridian suggested way to flip the bit. That second line there, the move sets the security bit. If they do that in the first 60 cycles, then the ADM 99.9% of the time doesn't work. Actually, sometimes it'll still.
It gets into a weird state, but it gets shut off.
Yeah.
But yeah, if you follow their instructions, then you will know exactly where it's set. So even if you've never seen a particular piece of memory or a particular piece of code, you should be able to predict exactly which instruction it is that is setting this bit. You're going to be the third instruction if you're using the default stuff. It's like a jump to one spot, then a jump to another spot, and then it calls this code block.
Yeah. And that is, the suggested way to do it is in every damn piece of documentation they have in the same way.
Right.
So you kind of know that every developer is just going to follow that and go, okay.
Right. We also don't necessarily care though, right? Because all we have to be able to do is get the processor to execute 30 instructions of any type without corrupting flash memory, I guess, but that's not going to happen on accident. And then the debug interface will come up. So you don't necessarily even have to be real specific with glitching, right? We could be. You could get in, you could glitch that very particular instruction and try to garble it, change it, or make the execution pointer go someplace else. But we don't necessarily even care about that because you can just let it just be crazy and do all kinds of stuff as long as it can survive for basically 60 cycles or whatever to let you bring up the debug interface and halt it before it resets itself.
Yeah. And so my original thought was having to be really precise, and then you reminded me we don't. So it became a hell of a lot easier, right? So we got. This thing's running at 10 meg. Originally, the original plan before yesterday was to hit only cycle 3, and now we don't really care. So we've got 2 approaches that we're working. We should have code that we hopefully release within the next month-ish, maybe 2.
Or even next week.
Yeah.
I don't know. We were hoping to have it up here for today, but we didn't quite get it working in time.
So, but we're going to have 2 approaches and kind of do a race to see who can actually pop it fast. So we're going to take the good fed approach of just flip everything. Just if we can get in a glitch state, we can stay in a glitch state for as much of that 60 cycles as possible. We really don't care.
Right. And so what we kind of mean by that, the good fed, it's a fantastic piece of hardware, right? We use it for all kinds of stuff. It's not extremely accurate. So if you're looking at the wave that's coming out the backside of this, it's not, at least in our experience, extremely, it's hard to make it line up correctly, especially when this thing's running at 10 megahertz and that's running at 16 megahertz.
Yeah. And then the other approach is a much more targeted approach with our shiny new hardware from the con. I'm hoping we can actually pull that off and do.
Yeah, we were working on this all weekend, so we haven't written any code for it yet, but we're looking forward to playing with that.
Yeah.
I guess the other side too that we'll just bring out real quick that we're looking at and that we're working on. We commented that this debugger here, it's like a $1,200 debugger, which really sucks for everybody. We would like to implement at a minimum certain types of functionality that you care about into the good fed. Right, so there are protocols that are in the good fed already that are relatively close to this one. We've got to finish, we've got to reverse out a couple of additional verbs that aren't there. We've got to do a couple other things, but anyway, we're working on that. We're hoping to have that out relatively soon too. And so we'd like to be able to do, logical operations like I want to be able to download memory out of this thing, right? So if you hook up a good FET in the right way, then it sucks it down.
Yeah.
So we'll see how fancy we get with that. But if the glitching stuff work, of course, that'll be implemented there as well.
But
anyways,
at least dump and write code should be there soon. We were really close until a couple days ago.
All right, 5 minutes to spare.
Questions? Early morning.
Everybody still asleep?
What's up?
You mentioned sort of like the production lag and things like that, and I've had some experiences in terms of trying to get eval boards and dev boards from various versus production. And I was wondering if you encountered any issues in terms of getting the eval boards that you have there.
So the question is, he's had issues ordering debug boards like this perhaps in the past, and was just curious if we had any issues. Maxim is really fantastic, so they're really great to work with. As a general statement, they seem to have a hard time keeping these types of boards in stock. So depending on the chip you're looking for, they can be either available or not. The thing that sucks about the Maxim site is that it's never accurate on either what's in stock or like how long it'll take them to get it. So I mean, when we ordered them originally, it said it'd be ready in 2 weeks. And then like 3 months went by and we still didn't have one. So finally we just switched. Not particularly. So IDA supports it, but not well, right? So I don't know. There may be others that would have something like that. So feel, come talk to us if you know better ways to do it. But it's painful. And the banking logic and some of that kind of stuff doesn't seem to work right. So obviously there's massive sections of code that are in other places that are both being called to and then have calls coming back from that IDA is just generally not aware of. And so you kind of got to manually do a lot of that, and it's painful. But cool. All right. Well, that's it. So yeah, come find us later if you want to chat or something.
Cool.
Thanks.